Okay. So say we have some machine that produces, I don't know, springs. Say we actually have 3 of those machines. Say we have 3 machines producing springs. And say that we take from that machine some arbitrary spring, right? So we make some draw from the springs that are produced from this machine. So let's say that the probability that we get some defective spring, so the probability that we get some defective spring, given that it came from machine 1, is equal to 0.02. Let's say that the probability that we draw some defective spring, given that it came from machine 2, is equal to 0.01. And let's say that the probability that we draw a defective spring, given that it came from 3, is equal to 0.03. Right? And let's also say that machine 1 produces 35% of our machines. So just in general, if we select a spring at random, the probability that we get one from machine 1 is equal to 0.35. Right? The probability that we would get one from machine 2, let's say that that makes 25% of our springs, and the probability that we get one from machine 3 is equal to that remaining 0.4. Right? We have to draw a spring, so these have to sum to 1. Okay, so we've got the probabilities that we need to work with. So let's say that we pick, well, let's ask this question. What's the overall probability of getting a defective spring, right? We know the probabilities if we condition on a certain machine, but just what is the general probability of getting a defective spring at all? So we reach in, we grab a spring, what's the probability that we got a defective one, right? So what is the probability of defective? Well, that is simply the probability of, or the sum of all the different probabilities of the different ways that could happen, right? So the probability that we get a defective and it's from machine 1 plus the probability that we get a defective and it's from machine 2, right? And the probability of defective and it's from machine 3, right? And this should be pretty clear. It should be pretty clear that these probabilities can simply be written like this, right? We just used this relationship when we were looking at Bayes' theorem just a moment ago. Right? So these conditional probabilities multiplied by the thing that we're conditioning on is equal to the joint probability. Right? And we have everything for this relationship, right? These machines are all disjoint, right? We don't produce a spring from 1 and 2 at the same time, right? So these defective springs are conditioned on these mutually exclusive and exhaustive events. So by the law of total probability, which is hopefully what you're seeing we've done here, we can simply write that the probability of defective is equal to this relationship. And so if we just take all of our constituent elements, so we need this probability right here, 0.02 times 0.35 plus 0.01 times 0.25 plus 0.03 times 0.4, right? I'm gonna write this in fractional form just so that we don't have to deal with a bunch of silly decimals going on here. You can check this if you want. But the sum of these things is equal to this fraction. So we haven't used Bayes' theorem yet. All we've used so far is the law of total probability, right? That if we have some mutually exclusive and exhaustive sets, events, I should say, and then we have some other event, we can describe that other event with respect to that mutually exclusive and exhaustive set of events. So if we take this and we say, okay, I want to know what the probability. So say that I draw some defective spring, right? Say that I reach in and I grab some defective spring. Well, what's the probability that it came from, say, machine 1, right? That's something that we can calculate, and that might be useful information. So say that I get some defective spring, right? And I want to know, so say that I have some defective spring, right? I've observed that, and I want to know the probability that it came from machine 1. Well, I can solve for that. I can say that by Bayes' theorem is equal to the probability of having a spring in 1 and it's defective, right? Or the same thing as the probability that's defective and it's from 1, right? Divided by the probability that it's defective, right? Which by Bayes' theorem is simply equal to, right, this sum down here that we talked about, which we found up here. So I guess I'll write it like this. Yeah, d given, well, we won't write it in summation notation because I haven't used any subscripts up till this point, so to spare us that, what might be confusing at this point to introduce notation, right? Times pi, right? It's probably overkill to write this all out again, but already this far, so hopefully you guys can see that we already have this right here. But the point is that where we're going with this is that we can write this whole thing, this probability of the probability that our spring came from machine I, given that it was defective, by Bayes' theorem is just equal to this thing, and we have all of these ingredients, right? So this probability is right here, right? So that's 0.02 times 0.35, right? And we're going to divide by that thing we found with the law of total probability, right? Right, because that's just the probability of getting a defective spring. And I'm not going to simplify this thing, I'll leave that to you, but we could write this whole thing in fractional form like this, right? And that's that. That's Bayes' theorem in action.